That's test 1, 2, 3. Stevie, can you hear me okay?
Yes, I can hear you okay, Lance.
Perfect.
Likewise, can you hear me as well, Stevie and Lance?
Yes, I can hear you as well, Dakota.
Also to confirm that you can see the first intro slide on my PowerPoint.
Yeah, we can see it, Lance.
Perfect. So far, so good, right?
Yes, I can see it from my end as well.
Good morning, good afternoon, and good evening to all of you. We are at 11 a.m. Central Time. Thank you so much for joining us today. My name is Lance Cizik. I am the Western Regional Sales Manager for HORIBA Instruments. Again, we appreciate you all being here today to learn more a bit about the Raman. I'll be one of the moderators on here. As you can see, there is a board off to the right where if you have any questions, if you have any chats, if there's anything that you would like to do regarding these applications, please feel free to log them there. Just a quick agenda on where we're going today. I'll be speaking briefly about who is HORIBA and briefly touch on some of the HORIBA products. Some of you may be familiar with them, some of you maybe not, but that's why we do these kind of things. And then once I'm through with that, I'll be passing it off to Dr. Dakota Morales. He is the product specialist for the Process Instrument Raman group. He'll dive a bit more into the product details, applications, support, and then after that, we'll have a question and answer session. Again, we would like to ask that you please hold your questions until the end of his presentation, or if you don't have the ability to wait for the end of the call, please do log them in the chat box that was provided when you logged in, and we'll try to address those on the fly. And then once after that, we'll kind of rehash what we spoke about. Without further ado, we'll kick this off. So some of you are obviously very well aware of HORIBA. We're based in Kyoto, Japan. That's where our CEO, our board of directors, that's where they're all located. We started back in 1953. We have greater than 7,200 employees worldwide in all of our divisions. It is a family-owned company, and we take quite a bit of pride in the fact that we are a family-run organization, and we've been doing that for quite some time now. So specifically regarding the Americas, we have 3 facilities, 2 that we work out more than one. There is the Irvine HORIBA Instruments Incorporated site, which some of you may be aware of. That's actually where the bulk of our accounting and our admin is. We have the HORIBA Instruments Houston, which is kind of the heartbeat of everything that happens regarding the analyzers that we provide, to where our integration, things of that nature happen. Some of our manufacturing as well. And then we have the HORIBA Process Instruments office, which is in Salt Lake City, Utah. That's where Dakota is, and he will be leading the call from there as well. Just to briefly touch on some of the analyzers that you may or may not be familiar with regarding the industrial process and environmental group. We have been focused for a number of years on gas analyzers on several different levels. Ambient air monitors, combustion control monitors, which some of you may be familiar with, the INDA 7000. It's a bit of a gold standard when it comes to SEMS analysis. Process gas analyzers. We also are widely known for our system integration, the ability to put our analyzers, or pretty much anybody's analyzers, into shelters, into racks, things of that nature. And then we have field services as well. So support is a very big part of what we do around here, and it's something that we take quite a bit of pride in as well. As many of you may know, last October, we made an acquisition to bring the Process Instruments group online and into the HORIBA family. It's been a fantastic thing for us, and hopefully a fantastic thing for them as well. It's really kind of brought us into a new realm. As you know, HORIBA for a long time, we've kind of been part of the regulatory environment, and so it's been kind of like a it's not a revenue generator for a lot of our customers, and that's where the Process Instruments group is really going to be able to allow us to make a massive change in what we do as a business. This is a return on investment analyzer, and it's quick, and it will help our companies make more money. As everybody knows, time is money, and being able to get quality data in a very short amount of time that can affect the process is exactly how you make that happen. Just to give you, again, kind of a 30,000-foot view, this is kind of a breakdown. Today we'll probably be more focused on refinery applications, and they will fall under these groups right here: gasoline, crude units, distillate monitoring, reformers, alkylation, the list goes on. So this will be the bulk of what Dakota discusses today. And just to give you just kind of a quick breakdown of who we are and who specifically, we're led by Dr. Frank Thomas. He's our Executive VP and General Manager. Brian Ross is our Assistant General Manager. Harsh Agrawal is our New Product Specialist. We're very happy to have him on board. And Giancarlo Aguirre is our Operations Manager for the Process Instruments Group in Salt Lake. Obviously, Dr. Dakota Morales is our Product Specialist. Mick Dolenmayer is my counterpart for the Eastern region, and then there's obviously my name there. So if you have any questions, obviously there's quite a bit of information right here, and you're about to get quite a bit of information. We are on all social media platforms. This webinar specifically should be posted on these platforms by the end of the week. We ask that you go to our pages on here, hit that like button, subscribe to it, and you'll be able to see the bulk of information there. Again, if you have questions, please hold them till the end, or if you'd like to put them in the chat box, we will address them as needed. And without further ado, Dr. Dakota Morales.
Hello, everyone. Can everyone see my screen here?
Yes.
Yeah, I can see
Yes.
it, Dakota.
Yep.
Okay, thank you. Okay, wonderful. So yes, Lance, thank you very much for the incredible introduction. My name is Dakota Morales, and I am a product specialist here for our Process Raman analysis for HORIBA Instruments Incorporated here in the United States. I'm very excited to be able to go through this introduction with you guys on the incredible technology that we have going on here. So our Process Raman is a part of HORIBA's Industrial Process and Environmental segment. We are located in Salt Lake City, Utah, but we belong to a very large global network of group companies for our Industrial Process and Environmental segment. Here in Salt Lake City, as Lance described, over here in red, and our international counterparts here across the world. So we have a strong backing across the HORIBA network. Last year, in October of 2023, HORIBA acquired Process Instruments, and we joined the HORIBA group company. And with that, HORIBA acquired over 25 years of Process Raman experience with Process Instruments joining the company. It was founded in 1994. We have over 165 online Process Raman installations worldwide. And within those installations worldwide, we are currently watching over 150 different process streams, all with different challenges, product lines, etc., giving us a wide variety of experience as we get into this Process Raman here. So for those of you that may not be familiar with Process Raman, I thought it would be important to go over some basic principles of the spectroscopic technique that encompasses Process Raman. So, of course, Process Raman is defined by the use of Raman Spectroscopy, which is a light scattering technique. If I can walk you through this figure here on the left, where the laser that is used in our analyzer will excite a molecule within the process stream, and the vast majority of the photons that interact with the molecule there, like a 99.9999% literally amount of photons, will just be elastically scattered. That means that they do not interact with the molecule in the way that an inelastic scattering would create and interact with a vibration within the molecule. And that is exactly the sort of unique spectral fingerprint that we are looking for in Raman spectroscopy. So we are able to determine the exact chemical components and makeup of a process stream because of the way that Raman spectroscopy interacts within our analyzers into the process stream here. So within Raman spectroscopy, a lot of people think of, mid-IR spectroscopy as sort of its counterpart because they do share the same vibrational modes. However, there are different selection rules between Raman and IR spectroscopy, which allows for different vibrations to be active depending on the technique that is used there. So to get a little bit more into that, here is an example of propane here, and showing the two Raman active vibrations in this molecule, which would be the anti-symmetric stretch and the symmetric stretch over here. And that really shows how the change in polarizability of the molecule allows for a Raman transition to be, a vibrational transition to be Raman active, versus in IR spectroscopy, it must require a change in the dipole moment. So just to show you that these sort of vibrations are what we're looking for in Raman spectroscopy and what allow us to see a unique spectral fingerprint in our spectra that we collect. So Now that we're through sort of the basic principles of Raman spectroscopy, it's important to actually get into what process Raman is here. So when I say online process Raman, I mean process Raman that is done on an actual process line in an industry. So not over the internet or something, but just on the line is the way to think about it. So online process Raman is essentially just applying Raman spectroscopy to industry. So process Raman is used throughout various industries to monitor chemical processes in real time without needing to disrupt any operations. So sort of a general workflow for real-time monitoring for online process Raman can sort of be broken down into these 4 steps here. So the first thing that we will do in a sort of general sense for when we're working with our process Raman is the very first thing is we decide on a sampling point with the end user. So a flow cell or probe is installed at sampling points in a process stream. And what I mean by that is we either take a flow cell enclosure and plumb from the process line into a flow cell enclosure where there's a Raman probe inside that enclosure that reads back into the analyzer. Or another option is using an immersion probe that goes directly into the liquid and constituents of the process stream, as sort of represented by this red arrow here. Next, after the process stream is interfaced with the probe, a laser beam is turned on, directed at the sample and process, and we generate that scattered light. And look for the inelastic scattering of the molecules, which generates our Raman signal. And then that data is collected because the Raman signal is collected by the analyzer to produce the Raman spectrum of the process, sent directly into our analyzer. And then last, process control. The chemical composition of the process is determined through chemometric modeling, which allows feedback through things like advanced process control software to optimize and control the process. So in today's world, there are a couple different, several different ways that, that processes are monitored in industry. One of the main counterparts, as I sort of alluded to earlier, to using Raman for process monitoring is using NIR. So I just thought this sort of side by side to walk everyone through these different features of the 2 different spectroscopic techniques. So a measurement type between Raman and NIR, of course, is scattering versus absorption. And this really affects the sort of spectral resolution that can be expected with Raman and NIR. So in Raman spectroscopy, you are always guaranteed to just scatter 1 photon per molecule, where in NIR, depending on the power of the laser, depending on the wavelength that you're using to use your NIR spectroscopy, you have the possibility of creating overtones in your spectrum, combination bands, which overtones are just when molecules absorb energy that correspond to multitudes of their fundamental vibrations. So you see a very messy, convoluted spectrum where in process Raman, you're just seeing a fundamental vibration on a 1-to-1 photon basis. Something else that process Raman really shines in is that there is no sample prep needed. And we'll get into that a little bit later, but as often required in NIR systems, very complicated and intricate sampling systems come along with the with the process monitoring, which further complicates things. Likewise, with water sensitivity, Raman is insensitive to water, where NIR is very sensitive to water and has strong absorption bands. With NIR spectroscopy, operating conditions, Raman can be highly adaptable, and by that I mean it's not temperature sensitive. The process can be turbid, and there's ways to work around those sort of things, where in NIR, the operating conditions are much more limited. It's very sensitive to temperature. There can't be a lot of particulates or other things that may interrupt a sample stream, which would throw off, collection of that data for NIR spectroscopy, whereas process Raman is way more adaptable to those sort of unexpected changes, we'll say. Calibrations for HORIBA Process Raman, I'll get into this a little bit later, but the calibrations for the instrument are all automatic. There's nothing that the end user needs to do before they collect the spectrum. The software runs through it automatically, whereas in a lot of NIR spectroscopy, their calibrations are manual, timely, and this sort of goes into the maintenance that is expected with NIR analyzers. That when a lamp is changed in the analyzer, that's expensive. It needs to be recalibrated that way. The optics are more costly, and also the detector is much more likely to drift over time with the sort of wear and tear of that instrument, where HORIBA Process Raman really has little to no maintenance, and I'll get into the history and the statistics on that a little bit later. So, I can't be so unfair to not talk about the elephant in the room when it comes to Raman spectroscopy, which is fluorescence. It is, known, and it's probably in a lot of people's heads that that fluorescence of a sample is a big killer in the, feasibility of Raman spectroscopy in a process. But with HORIBA Process Raman, we specifically choose laser wavelengths that will abate the fluorescence as much as possible. So here is a spectrum collected with 3 different laser wavelengths. The red is a 532 nanometer laser, and this black here is a 785 nanometer laser trace. And this is the wavelength that we use in our process analyzers now. And so as you can see, there is a large arcing baseline noise from the fluorescence with the 532 nanometer laser. But with the 785, when we walk it to much longer wavelengths, that baseline pretty much goes away completely, which allows for a much more resolved and tractable spectrum. Likewise, I thought I'd get into a little bit about the Raman spectrum of water here. So Raman is not affected by water because the water peaks appear at much higher peak shift wave number than a petrochemical Raman system, for example, or a petrochemical Raman spectrum, for example. So as you can see here down past the 3000 wave numbers, there's this big, broad absorption or scattering of the OH stretching modes in the water, and the HOH bending mode down here at 1648 wave numbers. And for a lot of the applications that we currently work with HORIBA Process Raman, all of the peaks that we want to look at are over here anyways. So when we can calibrate and model from, when the vibrations are down here at these peak shifts, we don't have to worry about anything to the right at all. We can just look right here, and therefore water is not an issue at all. So getting into a little bit of, what we offer and, what we would really like to introduce to you guys today with the HORIBA Process Raman. First, of course, is our analyzer. The sensitivity of the HORIBA Process Instruments analyzers makes it capable of detecting very low concentrations of substances, which is extremely crucial for our customers and end users who need precise and accurate measurements in their processes. So our low detection limit, we can get down to single-digit ppm. And this literally is the best in class for Process Raman right now. A lot of our competitors and a lot of other analyzers out there can really only get down to volume percents or half volume percents, we'll say, but we can readily and proudly get down to single-digit ppm with our process analyzers. Likewise, our fiber optic connections to our analyzers allow for flexible analyzer placement, which totally reduces installation requirements and constraints for an end user. So that headache can kind of be taken away if, we can set up that analyzer, up to 350 meters away from their process line. And likewise, as discussed earlier in that workflow slide, we can interface to a process with a flow cell or just a direct insertion probe for sampling. Likewise, with our sampling, there is no interference from water, particles, bubbles, or fluctuations in process temperatures. There's also no sample conditioning required with our Process Raman, and that is, in contrast to a lot of traditional analyzers where complicated sampling systems are required for the process monitoring here. Likewise, with our analyzers, we can get to 1 to 17 different sampling points from one analyzer. So you can look at up to 17 different sampling sites with just one of our process online analyzers, which is pretty incredible. And something else that we really pride ourselves on, and something else that our end users really look forward to, is our state-of-the-art chemometric modeling. So our chemometric models are easy to transfer models from laboratory to implementing them directly in your process, and they're very straightforward to integrate, regardless of how many analytes or components a customer or end user is looking at once. And this is something that we can begin to build with end users before the analyzer even shows up at their site. So getting into the Process Online Raman Analyzer here, as described earlier, there is a opportunity for it to be a multi-channel process analyzer where we can look up to 17 different streams at once. It also allows for multi-component per stream to be viewed here. And that's really incredible because there's minimal interference from water, temperature changes, gas bubbles, etc. And all of our certifications down here allow our process analyzers to be suitable for various hazardous and non-hazardous process environments. And we are fully compliant with ATEX Zone 0 and IECEX standards here. So getting into the sort of Process Raman products that we offer with HORIBA. So over here on the left is sort of our flagship product. This is our single point process Raman system, as well as our dual point process Raman system. And if an end user is interested in looking at 3 to 17 sampling points, we can interface the single point process Raman unit with a fiber multiplexer, which allows for up to 17 sampling points with just one analyzer. So this is very useful for large-scale manufacturing operations and also to reduce on capital costs overall. Likewise, with our sampling options here, this is a picture of that process flow cell that helps with inline process analysis without disturbing flow, perturbing, the sample stream, etc. If that is a worry or concern, where down here is an image of a typical immersion probe that it allows for direct insertion into the process line. So after this break here in this table, over here on the right side is sort of our offerings for a laboratory that fully complement the online analyzer here. So this is our flagship laboratory analyzer. We like to call it a QC/QA analyzer because it really excels at laboratory automation. Our Raman products are super helpful for developing and validating laboratory analytical methods, which go hand in hand with the modeling for our online analyzers. Likewise, with the different autosamplers here, we have a 42 vial liquid autosampler that is an option to be interfaced to our laboratory analyzer, as well as a 6-bomb LPG autosampler here. And this is just hardware tools for more automated analysis for our end users in the laboratory. Here is an image of our online analyzer that would be seen in a general purpose room, as well as a purged enclosure that can be built around the online analyzer. So this is just sort of demonstrating that the process analyzer can be set up in a general purpose room, or the Raman process analyzer can be put in a purged enclosure, which makes it suitable for like different zones and things like that, and can be easily installed regardless of the environment that the analyzer is going to end up being in. So here's a schematic illustration of how our multiplexer allows for multi-channel monitoring. And if I could just walk everyone through this figure here to sort of give the workflow of how this works exactly. So the computer up here in the top left controls this spectrograph, which is this gray box on the right here. And multiplexer, which is this rectangle in the middle, is used to collect and record the Raman spectrum at various sampling points. So for example, in a typical collection with an online analyzer, for example, we have 2 different redundant lasers installed in all of our online Raman analyzers to help extend the lifetime of the lasers, as well as offer a more secure backup where there is much less downtime, if any downtime, if one of the lasers were to fail, because there's a second laser that can just pick right back up where the other one left off. So depending on the laser that is being used, the light from the laser is interfaced into the multiplexer, and then from here, the multiplexer can send the laser light out to various remote sample cell points, excite and vibrate the molecules, and collect the Raman spectra back through a fiber optic cable into the multiplexer. And then this is read from the multiplexer back into the spectrograph, where that image is read onto our camera. And then that spectrum is brought from our spectrograph camera through a serial connection into the computer. And then that is where the results and parameters from our chemometric models are read from the image that was collected. So the long and short of it all is that this sort of workflow here allows the spectrograph to switch from one sample to another without requiring any reconfigurations of the hardware at all by the end user once we have you set up and ready to go looking at the sampling points that you choose. A little bit more into the multiplexer here. So we can monitor up to 17 different sampling points or sites with just one analyzer because of our in-house built multiplexer. And this ultimately allows for needing fewer analyzers overall because it reduces capital cost if you only need one analyzer to do all of those. We also technically, the multiplexer is interfaced with 18 channels, but we do reserve the very first one for a built-in performance channel. And the built-in performance channel ensures that the system is reliably accurate over time by using a performance sample, typically toluene, to diagnose and monitor key indicators of your analyzer's performance and health. If something is wrong with the performance sample, or if the performance sample spectra that is being collected is not what is expected, our software, our analyzer will realize that, recognize that, and flash a preventative warning to you regarding the analyzer, for example, which also helps reduce maintenance cost overall. And this also provides ASTM validation channel procedure checks, we can say, with this built-in performance channel. Here is a zoomed in image of our multiplexer with two different fiber optic cables interfaced into it. So this top one here is an SMA connection for laser excitation. So this is what brings the laser light to your sampling point. And this bottom one here is an FC connector shown in these images on the right here. And this is what brings the Raman signal back into the multiplexer, which then gets brought into the spectrograph. And we'd also like to point out here that these are quite large diameters for these fiber optic cables. And we do this because the larger the collection fiber, for example, the more efficient signal collection that we can achieve at the sampling site, which results in better signal to noise collection for the analyzer, which, for example, goes hand in hand with that low detection limit that our analyzers provide. Here is a little bit more information on the flow cell. So our customizable flow cell is intrinsically safe. It features a NEMA 4X stainless steel enclosure here and can continuously operate under pressures up to 35 bar, fit 500 PSI, in temps of -20 to 200 degrees Celsius. And NEMA here, this is a United States-based organization that sets standards for enclosure equipment like this in industrial settings. So some important components of our flow cell here is this sapphire window that is shown in this little diagram here. So this image here is shown is sort of a drawing of the cut through of this green box here is this. And so this sapphire window allows for diagnosing a dirty window cell. And also if the position of the Raman probe isn't perfectly situated up against the flow of your process, etc. And the analyzer would flash a warning to you that your model isn't to be, as expected, because the sapphire window will start showing a sapphire peak and really alert the end user that there's an issue with the flow cell here. And so this is just another diagnostic tool that we use. Likewise, our various flow meters and pressure gauges inside the flow cell enclosure ensures that the sample is flowing through the cell at your desired and constant rate. So an easy check to make sure that your stuff is going through the way that you would expect it to. Also, the tubing that we put in here is extremely straightforward. It's in, goes through, and then comes out. And that is, try to make it as simple as possible so that the long-term durability of the flow cell is increased by the lower amount of tubing that is used, and also depending on the corrosiveness of your sample, and also just the various standards that may be used in different industries and applications, we can modify the actual material that is used in this tubing here with our swage lock. Next is our immersion probe. So the immersion probe we also call intrinsically safe, and this can be installed directly in line into your process stream. The probe here is rated up to 210 bar or up to 3000 PSI of pressure, and a temperature range of -20 to 100 degrees Celsius. The probe length can be customizable between 1.5 to 3 feet, and that would be this distance here after the gland seal. And the gland seal that we outfit in the immersion probe ensures that no product or sample will ever leach into your immersion probe, which could, of course, bring the potential to messing up the optics that are inside the actual immersion probe and getting stuff stuck where stuff should not be stuck. So the gland seal really prevents that from happening, which allows your process stream to be safe, as well as the hardware for the analyzer to be safe as well. Getting into our laboratory equipment here, more images of our laboratory systems. So the benchtop laboratory analyzer here can be interfaced to a 42 station liquid autosampler or a 6-station bomb LPG autosampler, just completely whatever the end user may need for their applications in their laboratory. And the benchtop analyzer really is designed to help build and maintain model integrity for our online analyzers. So for example, and I'll get into this in a little bit here, but in a refinery, for example, if a customer has a different summer gasoline blend versus a different winter gasoline blend, and they are trying different blending procedures, recipes, etc., they can use this laboratory analyzer to help build chemometric models that can be placed directly onto their online analyzers. And also, separate from anything to do with chemometric modeling, the benchtop analyzer can also be used to measure routine samples within a laboratory efficiently and just enhance overall productivity. Likewise, a glimpse inside under the hood of the laboratory analyzer here, another schematic illustration where the computer triggers the collection of the Raman signal from the sampling point. So imagine this being the autosamplers, for example, where that signal is then brought back into the spectrograph. The camera image is read back onto the computer for a real-time analysis right here at this sampling point. So something that I mentioned earlier at the beginning of the introduction was our automatic calibrations. So our laser wavelengths, as we all know, lasers are not perfect. They do have the potential for wavelengths to drift a little bit over time, and the excitation laser drifting is not good for Raman spectroscopy because that will bounce the wave number shift around, for example. So when this happens, our analyzer will automatically recalibrate using known peaks of references. So this is the example spectrum of toluene. And this is one of our favorite features to use here, the 785.6 wave number vibration and toluene, sort of isolated and strong. We can use this to track and calibrate the laser wavelength so that the, accounting for any shifts in excitation laser energy when the laser moves. Likewise, an automatic x-axis calibration happens routinely throughout collection in an online setting. So this is an emission spectrum of neon, and the analyzer uses known peaks of neon to calibrate the x-axis. So all of our analyzers, laboratory or online, come with a neon card in its spectrograph, and this neon card is triggered on and off to as another internal reference in our analyzer to calibrate the x-axis energy positions, which correlates to the pixel locations on our camera. So that's always accounted for as well. Likewise, with the y-axis calibration, so intensity normalizations here, our analyzers come with a preset y-axis calibration based on the Raman probes that are interfaced to your analyzer. So here in Salt Lake City or at your, at your site, we calibrate the y-axis of the analyzer, and this calibration is only done once per probe that the analyzer collects on, and then is installed for all subsequent measurements using that Raman probe. So this is something that usually only needs to be done once per probe when it first starts. So all in all, really, the laser wavelength, the x-axis, and the y-axis calibrations essentially zeroes out any laser wavelength drifts, the analyzer's fiber optic systems, and the collection probes. And so these all positively affect the transferability of the models from a laboratory analyzer, for example, to your online analyzer. Here's sort of an overview of our ProSpec software. If you were sitting at one of our analyzers viewing the computer as you were collecting toluene, this is exactly what you would see. So at the bottom of the screen here is an image of the spectrum that is being collected at that time. Up here is the data window, and so this is where different parameters of your chemometric models get read out, like concentrations, different, if this was a refinery, different, or for gasoline blending, for example, different octane numbers, things like that. Information that you as the end user really care about is all read out up here. Up here, we have a very straightforward menu bar and operational buttons that allow for very quick and straightforward access for end users to get exactly what they want without having to dig through 100 different menus and searching and all of that stuff. Down here, depending on the different channels that the end user has set up, you can quickly click through the different streams to see what is happening on each of your channels. Likewise, down here in the bottom right is a call it our diagnostic way for the software to interface with the analyzer. So this is present on every single screen of the software. So any end user, regardless of what they're doing with the software, will always be able to see the laser information that the analyzer is currently running on, the different calibrations, how they're going, the temperature of the camera, and the status of the multiplexer if they have one, etc. Here is just sort of showing the different things that an end user might really care about with the sort of ProSpec diagnostics bar down here. It will always read out the laser wavelength, the current laser power, which we typically keep at 450 milliwatts, the camera temperature, which we cool down to a very cold -81 degrees C, and that really helps with the noise of the camera and overall helping our signal to noise ratios. Our minimum counts here on the y-axis of the spectrum that you're seeing, likewise with the maximum counts, and this is shown with this 1004 wave number peak of toluene here, so this reads that, as well as in this data window, this is just an example showing the M distance of the model, and the M distance is just another way to describe how well is the spectra that is being collected represented by the model that is installed. So sort of, moving on to the sort of workflow of how chemometric modeling may work for the end user here. Raman models are, first generated and then used for validation. And this is sort of the process of how that happens. So samples are collected and then analyzed in the lab here. So for example, collecting a sample from the flow cell or preparing samples before the analyzer even, gets to the online analyzer even gets to your site, and users can collect samples, send them to us, use a Raman analyzer, use the laboratory Raman analyzer, a demo unit, etc., to build models, collect Raman spectra and data files. So they can perform routine lab analysis on these results, give us the data from those results, collect the Raman spectra from those results, and then that's how we can build a chemometric model. And then this completes the cycle of how this model can be installed directly onto an online Raman analyzer, even if it was collected with the laboratory one, regardless of where that is. And this can be applied to the distributed control system for the refinery for process control. And likewise, as I mentioned earlier, if the model isn't doing a good job at representing a new process or a new something that may have happened in the industry setting, that can be reapplied back into the laboratory Raman analyzer to figure out and rebuild that model and reapply it into here. So just sort of like a circular way of building these chemometric models to provide real-time data for efficient process control ultimately. So some applications of Process Raman that we really, pride ourselves on being able to be interfaced into various, sectors of industries. Our bread and butter here with HORIBA Process Raman really is the petrochemical industry. So that includes oil and gas refineries, chemical plants, upstream solutions. So offshore rigs, for example, things like that. Aqueous-based applications, so life sciences, pharmaceuticals, water applications, wastewater applications, recycling water applications, things like that, as well as the food and beverage industry can really benefit from, interfacing Process Raman into their monitoring needs. And of course, a lot more things like polymers, renewable energy sectors, semicon, which is obviously huge right now, can all benefit from Process Raman. Today, I'd like to sort of walk you through the bread and butter, as I said, of the petrochemical industry using our HORIBA Process Raman instrumentation. So we really pride ourselves on having a very large and loyal customer base. There is a good chance for, any customer that first works with us, they become a repeat customer because of the, sort of service, the sort of things that they can use for process monitoring with our analyzers. And these are images and the brands of the sort of, energy and oil and gas refinery groups that currently are using our analyzers today. So the sort of refinery processes that we like to monitor in these refineries start with distillation. So for example, as crude oil is brought into a distiller here, and as the lighter fractions of the petroleum are brought to the top, the middle, distillates down here, and then the heavy stuff down here, we can use Process Raman to help monitor the different cut points for each of these fractions, which allows for much more efficient separation of the different fractions of the petroleum, which allows for the right things to go to the right places in the refinery. And that's very helpful for saving money, for increasing production efficiency, etc. Next, once these fractions are brought to the right places within the refinery, they get converted into high octane constituents, things that are actually useful for a refinery. So these get broken down into 3 different conversion processes. The first is cracking. So that's just taking something like this aromatic molecule here, breaking it down into a much more simpler constituent, which can be brought into something like jet fuel or kerosene, for example, or even worked into something like p-xylene or n-xylene, something like that. Next is alkylation conversion process, and this is just the exact opposite of cracking, where they take the lighter fractions and then build them on top of each other to make more desirable blending components with higher octane numbers. And likewise with reforming, this is just a process in a refinery that will take a molecule that would be a low octane number, which ironically, this is octane here, and then moving it, reforming it into an isomer of octane with a much more higher octane number, which makes it a much more desirable and profitable molecule for the refinery. And in literally all of these conversion processes, we have Process Raman helping refineries optimize these conversion processes right now. Likewise, after the molecules that are created or the desired molecules are created in the refinery, they lastly go into the final product tailoring of the refinery, which is the different blending applications for gasoline, diesel, jet fuel, etc. Here in this image, you can see this is sort of a schematic of component tanks on the left, so different feedstocks that go directly into the blenders. And then these blenders can be siphoned into product tanks where product is stored over time, brought to trucks, wherever else it needs to go from the refinery. And process monitoring can be used at every single break between these different tanks here to make sure that it's flowing the way that it should, blending is happening the exact way that the refiners need it to, etc. And so this brings me to a main benefit of HORIBA Process Raman for refineries and petrochemical industries is you are getting a return on investment. We're not selling or trying to base our stuff on the environment or meeting some sort of regulation. We are helping with return on investment. So we'll start at the top of this cycle here, where CapEx for HORIBA Process Raman are generated and it gets installed. And this allows for someone in the petrochemical industry to obtain real-time data, which drives optimization of refinery processes, which, as mentioned earlier, creates reduced downtime and maintenance cost from, being able to predict when something is off in your process line or when something is off in the analyzer because it's thinking that something is off in the process line. And this immediately transfers into enhanced product quality and yield, which ultimately creates increased profitability for the petrochemical industry. And this allows our loyal customers to create even more CapEx for another analyzer in a different spot in the refinery, or talk to their friends at their refinery in another state, for example, and generate interest that way. So this is really just to demonstrate that the main benefit of using our Process Raman in industry is the return on investment that you achieve with it. Likewise, we also, solve operational problems, which also goes into that return on investment. So some operational problems in the petrochemical industry is when off-spec product batches happen, and that creates inconsistent product quality, which is not good for any seller, let alone of something like the petrochemical industry, right? Likewise, unplanned downtime, obviously we can all relate to any of our analyzers or anything that we need to help do our jobs. When that goes away, that's always inopportune, and even worse when it's unpredictable. Likewise, inefficient process control is born from inadequate real-time data in a refinery, and likewise, high maintenance costs take away from the overall profitability of any sort of industry. And that can come along with frequent and timely maintenance. HORIBA can solve these problems. Real-time monitoring allows for immediate adjustments. So if, for example, a refinery has our analyzer read into their advanced process control system. This allows for immediate adjustments in their blending operations, for example, to help re-get the sort of specs that they need for the blend that they're looking for. Likewise, our analyzers offer early detection with proactive instrument diagnostics. So for example, if laser power starts dropping, it will immediately alert the end user, turn that laser off, kick the redundant laser on and keep it on to ensure that a laser failure would never bring your system down, as we can ship you another one. Likewise, as I've stressed for sure, the optimized process control allows for more efficient operations, more product, and overall, we solve a lot of problems by just reducing the requirements that a refinery needs to achieve the data that they want. Minimized equipment wear and tear, and there's no need for invasive sampling systems that are complicated, require their own calibrations. You know, a statistic that we like to say is 90% of all issues with traditional analyzers in refineries nowadays are all from the sampling systems that are required with those analyzers. No sampling system whatsoever with HORIBA Process Raman. So just to wrap up here, some key advantages here to sort of summarize what we've just gone over. You know, our brand, you know, really provides analyzers that accomplish low maintenance direct Raman measurements with a very wide detection range from single digit ppm to, of course, volume percents. Our analyzers account for wavelength tracking corrections, intensity normalizations automatically. And we also offer state-of-the-art chemometric modeling support that offer themselves as fully transferable and that are self-consistently developed and applied to your process and your samples at your site. Likewise, we, of course, offer on-site installations and training for all of our analyzers. We won't leave until you want us to leave. So yeah, we will stay as long as needed to train and commission the important key staff members on the analyzer. And we really pride ourselves in making your staff the Raman experts that we are as well. Likewise, historically, this is a real statistic. Typical maintenance on our online analyzers is about 2 hours per process stream per year, which is very low and minimal. So thank you very much for tuning in today. We will continue our webinar series on Process Raman, and this is a main way to keep you up to date on new products, different application overviews, where we will go in depth into, you know, the sort of workflow, the sort of payback, the sort of information that can be achieved with HORIBA Process Raman. And please feel free to contact us, take a picture of this however you want. If you need to get in contact with me, Dakota, with Lance, our Western Regional Sales Manager, or of course with John, who is our Operations Manager here in Salt Lake City, we, all three of us, would be very excited and happy to you know, move any conversation forward and help answer any questions that you may have. So yeah, so thank you very much for tuning into the HORIBA Process Raman introduction today.
Thank you, Dakota. Very well done. Very informative. I want to open the floor now to anybody that has any specific questions related to the presentations that we just offered.
We do have 2 questions from our attendees. The first question is, can this be placed in hydrocarbon process stream from Derek Quinn?
Yeah, certainly. Yeah, hydrocarbons is definitely our sort of bread and butter here with our Process Raman. The vast majority of our applications involve hydrocarbons and the processes that involve them. So yes, the potential and feasibility of a hydrocarbon application is extremely high.
Thank you, Dakota. And the second question we have, what is minimum and maximum flow rates possible through the probe?
Okay, that's a great question. Usually we try to decide on 3 to 6 liters per hour through the tubing is sort of what we recommend. I have heard of situations from our manufacturing engineers where they work with customers that want fast flow rates like 8 liters through there, but we mainly the typical configuration, I'll say, is about 3 to 6 liters per hour.
Thank you, Dakota. And so
Actually,
we
Dakota,
do
I
have
have
a
one
survey
quick
after
question
this
I would
as
like to
well.
ask you real quick, if you don't mind. Is
Of
there a
course.
limit? Is there a limit on those hydrocarbons? I know some people may be concerned about running heavies through the stream. Is there an upper limit as far as what the Raman can handle?
Yeah, so that's a great question. I would say that the upper limit is honestly would be defined by the sort of color that gets created with the much more heavier hydrocarbons. Of course, you know, the darker a sample, the more likely it is to fluoresce with Raman. So in a lot of typical you know, applications in like diesel, distillates, jet fuel, gasoline, etc., those are more lightly colored. So that's very feasible to probe with Raman. But in the sense of an upper limit, I think that'd mainly be held by the sort of color of, you know, the heavier hydrocarbons, certainly. However, we are currently, you know, developing instrumentation and different sort of ways to solve that problem for things like lube oils and things like that in the very short term, actually. So that sort of upper limit on the heaviness of a hydrocarbon or the viscosity of it, for example, this is a short-term sort of plan for us to solve those operational issues in refineries right now.
Excellent. And I would also like to encourage people, if you did not see an application that you think might qualify for this particular type of analysis, please don't be afraid to reach out to us. We're always looking for new and exciting ways to use our analyzers. So if you have a question or if you have something that you think might work, give us a shout. We will for sure listen and do what we can to maybe come up with a new solution for you.
Yes, absolutely. That's
We
something
do
that
have new
yeah, we really look forward to is, you know, application evaluation, determining things. Yeah, we really pride ourselves in working towards that. So thank you, Lance, for mentioning that.
Absolutely. Stevie, did you have another question?
we do have more questions from our attendees. What is about sample temperature above 300?
Yeah, so the way that our current specs are for our flow cell enclosures and our immersion probes, the main temperature on the flow cell enclosures is about 200 degrees Celsius, and then the immersion probes would be are basically only rated up to 100 degrees C. So a temperature stream of 300 degrees C would be a little high for honestly any Raman probe, not just ours. But depending on the sort of situation that's in, we can talk more about that if you were to contact one of us. But the exact temperature ratings now are 200 degrees C for our flow cells and 100 C for our immersion probes.
All right. We have another question. What is the prospect of adding 1064 nanometer NM laser to your system?
Yes, very, very high, actually. This is something that we are developing currently and actually very, very far into the process of it and really working towards, you know, interfacing the 1064 nanometer spectrographs that we have now into our online analyzers. And so that's sort of what I was alluding to earlier when Lance asked about the sort of upper limit to these hydrocarbons. You know, the 1064 nanometer laser will really be key to looking at some darker turbid samples. So yeah, when that's ready to be released and we are finishing our R&D on that, like definitely tune into the webinar on the 1064 nanometer analyzer.
All right. Next question: can the probe be used in outdoor environment?
Sorry, I'm so sorry, Steve, you cut out at the very end there. Can you say that one more time?
Oh, sorry. Can the probe be used in outdoor environment?
In that sort of case, we really recommend doing the sort of flow cell enclosure to completely isolate the probe from any sort of external, weather, things like that, in like a covered area. So we, in a lot of our refineries, those flow cells are outside, and things like that. So the idea that it could be used outside, it can really be fixed by using a flow cell here. It's the way that I'm thinking about it is it can be mounted on a panel, for example, outside.
All right. We have a few more questions. With the extraction type sample system, do we need one for each of the 17 sampling?
So can you repeat that? I'm sorry, Stevie.
With the extraction type sampling system, do we need for one of each of the 17 samples?
Yes, I understand. Yes. So for example, if you wanted to look at 10 different sampling points, you would need 10 different immersion probes, one for each sampling point. So each sampling point gets sampled from the flow cell enclosure or immersion probe, but can all be interfaced to just one analyzer.
All right. So we do have another question. How about response time while measuring 17 streams all together?
Yes, so that's a great question. Thank you. So the sort of response time there is really up to the end user, depending on how long the signal needs to be collected for at each sampling point, as well as the order of the sampling system or the sampling points, how the multiplexer and spectrograph cycle through everything is 100% determined by the end user. Our software comes with an auto cycling script. So if you needed to look at a random assortment of channels, they don't have to be in tandem based on the number of the channels. The end user can type in the response time as well as the order of the channels that it views.
All right. Another question, how high can the temperature fluctuation be without any influence?
That's a great question. So I don't have it included here, but I would be more than happy to show you this data. This is something that is very interesting because we've shown with a 50-degree Celsius fluctuation in a gasoline blending model that there is virtually no difference whatsoever going through essentially a 50-degree Celsius temperature fluctuation. You get the same exact octane number, distillation information, et cetera, like that at the different temperatures within that range. So yeah, I didn't include it here, but in the next webinar on gasoline blending, or if you contact me directly, I would be very happy to show you that data.
All right, we do have another question. Is laboratory solution also equipped with similar spectra as coupled Raman?
Yes, so the Raman spectra that gets collected with our laboratory analyzers and our online analyzers are the exact same virtually sort of collection that happens. It's the same software, virtually identical spectrographs, like the actual guts inside of there. It's just mounted a little differently depending if it's in the laboratory or on the rack of the online analyzer, for example. But essentially, if you walk from the laboratory, see Raman spectra there, and then walk to the online analyzer, it will look like the exact same thing, just two different analyzers.
All right. The next one would be, what is the lifetime of the laser?
Yeah, that's a great question. So in a situation where the laser isn't running all of the time, the lifetime is greatly extended in that situation. For example, with the redundant lasers of the online systems, we like to say that the average lifetime is about 3 years in the laboratory analyzers, where the lasers wouldn't be on all of the time. It basically be like double that, so about like 6 years for a lifetime of the laser. And something else that I'd like to mention too about the lasers is we purposefully design them to be plug and play, so there's no alignment or calibration needed when a laser goes down and we send you a new one. There's only 3 things you have to plug into the laser at a time. And so that is helpful for when, you know, a laser dies and, you know, you need a emergency get one from us and we can send it to you.
Okay, we do have one last question. What is the max temperature delta the sample system is allowed to drift?
So that's a great question. Thank you. I think that I think over the history of the systems and streams that we've looked at, it's basically been about like a 50-degree drift that we've tried to model and look at. We don't usually, you know, see processes that drift much more than that, but in most cases, it's about like a 25-degree C difference where we don't notice changes in model performance, but hierarchical models, for example, can help you know, work through that, but definitely about plus or minus 25 degrees C, where we don't notice like a huge change in a model performance for a process.
Okay. Thank you, Dakota. That's all the question. And I do want to mention that we do have a survey coming out via email for everyone. If you would like to give us some feedback regarding this webinar, as well as what we would like to discuss next in terms of the webinar series for the Raman Process Raman products category. Yeah.
Excellent. Actually, I would like to defer back to one question where they talked about putting the Raman in the field. Obviously, that would not be an optimal scenario, but with the fiber optic being, or the fiber sample line, there being no limit, sometimes that's not a reasonable expectation as far as where they originally intend to put the Raman analyzer. Our integration group out of Houston would certainly be interested in exploring the option of putting some sort of putting the Raman in some sort of HVAC controlled cabinet that could be more, I guess, reasonable from a perspective of installation. So again, this would be something along the lines of give us a shout, and we're always willing to explore options from that particular scenario. Okay, well, if there aren't any more questions, again, I would like to remind you, this presentation will be posted on all of our social media platforms by the end of the week. We appreciate all of your time. We hope it was informative, and please do fill out the survey that Stevie will be sending out. And it doesn't have to be Raman analyzers as well. Obviously, that's a big focus for us right now. But if you have another webinar series that, if you have another webinar topic that you'd be interested in us exploring, we'll definitely take a look at it. Okay, well, I hope everyone has a fantastic day. Thank you, Dakota. Thank you, Stevie. And again, I thank everyone for their time. Have a great day.